We continue today to talk about incompressible flow over airfoils, and last time we elaborated two methods: calculation of symmetric airfoil and calculation of cambered airfoil, not symmetric. For symmetric airfoil, it was simple that lift coefficient was CL equal to 2 pi multiplied by alpha, linear function. And for cambered airfoil, as we already saw, it's equation 57, also proportional to a constant 2 pi and proportional to alpha, with addition of shift on angle, which is alpha L0, angle of attack at which lift is equal to 0, calculated by equation 61 integral function. When we elaborated this result, we could see calculation of momentum coefficient over the leading edge and calculation of momentum over 1/4 chord and center of pressure. Today we will talk about first aerodynamic center and then numerical method calculation of airfoil by results of calculation by vortex sheet. Aerodynamic center is the point at which we have lift and drag forces applied, so reaction force, right? And momentum we know also can be calculated. Aerodynamic center is different from center of pressure. Center of pressure is just a point at which pressure forces are concentrated, and the aerodynamic center also deals with friction forces. So it's a pressure and friction which creates lift and drag, can be converted to momentum around any arbitrary point when we know aerodynamic center. Equation to calculate momentum, the aerodynamic center with reference on 1/4 chord is shown in equation 67. And applying the theory of thin airfoil and cambered airfoil, we might see equation 71. Equation 71 is explaining to us calculation of aerodynamic center when we know two parameters, M0 and A0. Here, M0 is a momentum slope, is a function which describes change of momentum. I think I did not put here this equation, but I can write here. M0 is dm by d alpha, a lift slope, momentum slope, describing how momentum is changing with respect to change of angle of attack. And A0 is a lift slope. A0 is the CL divided by the alpha. Okay. Okay. At 1/4 chord, this momentum is calculated. When we know these slopes of momentum and the angle of attack, aerodynamic center of pressure can be calculated according to equation 71, as Anderson shows to us. Usually, aerodynamic center is located near to center of pressure and is close to 1/4 chord for most of airfoils. Here we can see two examples of this statement. On figure A, you can see NACA 230XX, and here XX are describing to us different variation of thickness of airfoil, starting from 12 to 24%. And same for figure B, airfoil NACA 64 to XX, where XX also describing thickness from 5 to I think 21%. We can see that for case A, aerodynamic center is located at approximately 24% of chord and decreasing with the increase of thickness of airfoil approximately to 22% of chord. So variation is not so high for different thicknesses. And I think this is made for zero angle of attack. Probably it's for zero angle of attack of this airfoil. And for another airfoil is B. Aerodynamic center is located at approximately 25-26% at small thickness of airfoil from 5 to 10%, right? And then it increases to 27, a bit more than 27%. So variation is also not so high, 25-27%. Comparing case A and case B, we see that depending on shape of airfoil, we can observe increase or decrease of aerodynamic center position. So it's not obligatory, we'll have to increase or decrease. For different geometries, behavior will be different. Can be more linear or can be more close to parabolic function, as you see on case A. But always reference value is 25%. We can see on case A, 25% is right here, 0.25. And for case B, 25% is here, 0.25. So it's the reference for both cases. Must remember when we calculate any airfoil, and this is was one of questions I asked when I evaluated work one, why in many cases position of center of pressure, which is close to aerodynamic center, was very, very different from 25%. For some cases, it was negative even, meaning that center of pressure is outside of the body. How is possible? For some calculations, it was on the other side, more than 100%, so also outside of the body. I understand it's possible because we use directly calculation mathematically, right? But mathematics and real life physics are two distinct things. We must filter information. Please let me know if you have questions about any discussion we have today, or about discussion, or about work you make at home, or about videos you saw. And I will try to explain you here. Next topic is numerical method, which uses vortex panels to describe airfoil lift and distribution of flow around airfoil. This panel method is an advanced way to calculate flow around airfoil and to obtain lift for such airfoil. This method is a more general method than we saw on lifting line theory. Lifting line theory is simplified from what we will discuss here. It's more general. It's more general. Idea of numerical method standing behind this concept is relatively simple, even though if equations may appear a bit complex, the idea is simple. We have to remember an idea in the following way. We always can say by words. In aerodynamics, we can explain all by words. Here, the idea is the following, that velocity created from infinite will be compensated from infinite direction, will be compensated by a vortex generated on airfoil. That's simple. So we have velocity impact from far field. This is this can be seen on, for example, equation 78 here. This velocity created from infinite direction, and it impacts our airfoil. It impacts in such a way that it cannot cross airfoil. That's it's simple. So normal component of velocity V infinite, I will draw on figure 32. Will be this. It will be V infinite and will be always compensated by vortex created on airfoil. I will draw opposite created on airfoil. Does not mean that this vortex, this velocity is created by a panel. No, this velocity is created by all panels. All panels contribute to velocity at each point. And this is Vn. Vn. Okay, so I hope it's clear. We can just compensate two velocity components. Once this compensation is provided, our normal component of velocity on the edge of airfoil does not exist, and we have just tangential velocity veta, which goes exactly parallel to flow, to the wall. Okay, this is one rule, very simple physical concept. We just compensate velocities. And second idea we must remember is not Runge-Kutta method, but Kutta condition. I also remember Runge-Kutta because actually Runge-Kutta method, you know, it's famous and it was created to solve differential equations and also used a lot in aerodynamics. But Kutta condition is here. We know that circulation or strength of vortex on the trailing edge of our airfoil should be compensated. So gamma I and gamma I minus 1 in total will be same. Will be same value, but opposite in direction. So they will compensate each other. Total circulation on the trailing edge is equal to 0, and this will guarantee that our stagnation point will be exactly on the trailing edge. So these two things we remember, right? Velocity is compensated, and Kutta condition guarantees that flow will exit from trailing edge of our airfoil. Now let's elaborate all these two simple ideas. First, compensation of velocity. Velocity from infinite direction is related to inclination of body with respect to flow direction. This is shown on equation without number, which I just mark with the rectangle. It says to us that the normal component of velocity at any panel would be equal to infinite velocity, which is constant, multiplied by cosine of beta I. This beta I is an angle between velocity direction and panel direction. Normal direction. So this part is going from infinite conditions, and velocity generated by vortex on airfoil is shown on equation from 72 to 76. On equation 72 is a potential function generated by potential function at each panel generated by vortex distribution over this panel. Vortex distribution must be integrated to calculate potential function on the panel, but since it's constant, we know that we will, instead of integration, use just product. So this is why gamma in further equations, in equation 74 and 75, will be outside of integral, because gamma is constant on each panel. And also there is an angle to calculate, angle between arbitrary point and the point of our interest. Arbitrary point is having coordinates x and y, and point on panel is xj, yj. And we are calculating this angle in polar coordinates to obtain change of potential function. Okay, once we do this integration in a numerical way, instead of integration, we use a lot summation with some influence from all panels. You can see this sum of potential function on all panels. Once we put formula instead of phi, we will find some part constant, constant, but outside of integral. This is why outside of integral, and some part which is a variable related to coordinates. Our coordinates change from one point to another, so they cannot be outside of integral. And written in this way, it can be solved numerically. I say numerically because to find velocity or normal component of velocity calculated, created by each panel, we must take a normal direction derivative of potential function. This is equation 76. We take our potential function, take derivative on this function in direction of normal or perpendicular direction to each panel, and we obtain Vn, normal component of velocity. As you may see, this Vn as a function of phi is counting on all panels on the airfoil. So all panels contribute to generation of velocity Vn. In such way, we can find this value. Then, since integral of theta ij ds is related only to coordinates, as you can see from equation 73, this integral is a constant value, and for each panel choice, I mean between one and the other panel, we will have just a constant in our equation. Instead of having integral, it becomes just a value. And for each particular panel, we can write this balance of velocity. On the left side of equation would be velocity generated from infinite distance, and this is totally constant, will not change because all parameters inside are constant, V infinite constant, and beta is constant geometrical angle. And on the right part of left side of equation is one parameter unknown for each panel, and all other parameters are constant. 2 pi constant, and J is constant calculated from integral. Such equation is written for each panel on our system. So number of equations would be equal to number of panels minus 1, because to satisfy Kuta condition, we already have last equation according to Kuta condition written on the lower right side of my screen. These equations are linear equations, algebraic linear equations with coefficients which can be solved if number of panels is not big. Could be solved exactly. There are very efficient methods to solve exactly equation systems of this type, and they are, I think they are bi-diagonal, or yeah, they are, or at least yeah, we can reduce to bi-diagonal or tri-diagonal equation system here. And if number of panels is big, we can use numerical method. For example, Gauss-Seidel method or new method of Newton to calculate and to solve this equation system. So our equation system is formed by number of equations similar to 4.80 and complemented with the Kuta condition at the end. Simple. Theoretically simple, just need to find beta, need to find these geometrical integrals and can solve. Such approach is successfully implemented in several softwares, especially in Airfoil, which I hope everyone knows, at least people who work in a competition team can use this program to calculate lift or many parameters according to model of Vortex sheet and other models as well. It's not the only method which is implemented in Airfoil. After we solve equation or equation system for 80, we will obtain as a result our unknown gamma values. What we do next with these gamma values, we can integrate, or in the case of numerical solution, instead of integration, we will just calculate sum of products, where we will summate for all panels, and the product would be strength of each vortex on each panel multiplied by size of panel. Once we do this summation, we obtain gamma circulation over airfoil, and then using Kuta-Zhukovsky theorem, equation 83, we will obtain our lift over airfoil numerically. I would like to show you that this part here is identical to this part here. So circulation. Okay. We obtain lift, but not just lift, which we are interested in. Once we obtain gamma values, we can go back to equation 475. I'll use another color here, and substituting to equation 475 gamma values, we obtain potential function, and as a result, we can obtain velocity components and pressure distribution and pressure coefficient distribution as well. Simply taking derivate or calculating derivate of this potential function. Once gamma is defined, numerically we can define u, the component of velocity vector, and Cp and pressure. So all parameters we need to know except parameters of boundary layer. You know, boundary layer is not included in this model. As an extension of this method, we can improve accuracy. Not we, but there is a method to there is a way to improve accuracy of vortex panel method when we define not constant values of circulation on each panel, but we define variation of circulation on each panel from 1 value to another. For example, as you can see here, control this panel has two values, gamma 1 and gamma 2. In such a way, we define linear distribution of circulation over each panel, and it improves quality of solution and it makes solution more accurate. In such a way, we have so-called second order approximation of gamma. Much better solution, more performant, let's say. And this method is also, I hope, is implemented in last versions of Xfoil. There are also other methods of improvement. For example, instead of linear function could be used parabolic distribution of circulation, but they require more computational resources and they are more sophisticated. And I think nowadays they are not so much used because an alternative method to this one is numerical simulation or CFD, which gives better results, better. Please let me know if you have questions or if you know why CFD provides better results than panel method. Please write in the comments. I'd like to understand if you know. One example. Meanwhile, I will explain you this. This is an example which shows us second order panel method compared with the classical solution is CFD. We see that it's quite well corresponding to a solution to panel method, CFD and panel method. So we can trust in many cases panel method. It's simpler and allows us fast to obtain distribution of at least pressure coefficient and lift. Which are advantages and disadvantages of this panel method? Why we prefer CFD instead of panel method? There are a lot of discussions about. Main advantage of panel method is that it's simple. So it does not require a lot of computational power. Solution can be obtained fast because to calculate according to panel method, you choose system of linear equations and at most some system involving differential equations, ordinary. So solution is fast. It's does not require so much memory also. And the disadvantage of this method is just because it's simple, it does not account on all processes. For example, we cannot calculate viscous flow. We cannot obtain drag associated with viscosity, because you know that inside drag force, most part is viscosity and smallest part is pressure. So with this method, we cannot calculate drag, we can calculate just lift. And also this method, because of this limitation, cannot evaluate any interaction of flow with the wall, for example, friction. And probably you remember that in the book we have a topic, is there a lift without friction? And as a result, Anderson says that, of course, if there is no friction, there is no lift. But how we obtain lift if we do not have friction inside this model? The answer is that our model is already an approximation, it's not a real process. Our model is a mathematical way to explain physical things, does not correspond exactly to a real flow. So this is why we can obtain lift without calculating friction. And also another limitation, do not forget that such method can be used for small angles of attack, which has no flow separation. So can be used for airfoils, cannot be used for flat plate, because for plate we have flow separation immediately when angle of attack is not zero. And because of this problem, I see nobody else answered the question, but okay. Because of this problem of flow separation, CFD is always preferable. Of course, CFD has disadvantages as well. That it requires computer. Nowadays is not a problem, but it also requires proportional time to elaborate simulation project. Probably you already understand how long you need to study to make good quality simulation. And I hope soon you will deliver work too for evaluation. Not very soon, but I hope that many people will deliver work too for evaluation, and this is just the first step. But with all this effort, we can calculate viscous process, we can calculate boundary layer, we can calculate flow separation, and quite accurately. So there are advantages on CFD, and the main advantage of CFD that you can use our fundamental equations directly to simulate flow. In case of potential equation and result we obtained from model we discussed today, we are not using directly this equation. It's an approximation. It's more distant approximation than Navier-Stokes equation, for example. Navier-Stokes equations are more closer to real process, but still not exactly the real process. Probably you understood that to describe flow in its all complexity is not possible by any mathematical model. For now, even the most sophisticated numerical and mathematical model are only approximate to solution. They do not describe exactly this solution. It is not possible. So there is no equation system for that. This is why we have many models, we have different approaches, and then we compare, validate these different models. We choose the most appropriate one from point of view of accuracy, time, our capabilities, costs, and we choose one which is better. And I think it's this tradition, this strategy will be used for a long time. There is no way to solve all by a single model, by a single method. Okay, since we discussed a numerical method to calculate flow distribution, we can talk about low speed or modern low speed airfoils. This calculation has also relation to our previous discussion, because only with the modern method of calculations these airfoils can be built. How modern airfoils are built? You have almost unlimited computational power nowadays with the highly performant computers, and with these computers you can calculate almost any geometry of airfoil. We can vary many points. We can change point by point to improve solution, to increase its characteristics. For example, as you can see here, lift coefficient is increased. There are two different airfoils. One is old airfoil NACA 2412, which is quite distant, quite simple airfoil. It's widely used, but it's not new, it's old. It has 80 years more or less, or more than 80 years already. And it's old. It was created when Aerodynamics was still being developed, but then with new computational methods, it's possible to improve. It's possible to optimize, testing many different configurations. So low velocity, high efficiency airfoils are done by numerical optimization of existing airfoils. So as a base, we use an airfoil which works good, and we would like to improve this airfoil, starting to modify its shape geometry for different conditions, for different angles of attack, for different Reynolds number, for different Mach number. And this, with change of geometry, airfoil can start working better and can start working worse, like lift to drag ratio will be better, higher or lower. When it improves, we find that airfoil is better, right? So when it decreases, this ratio is not so good. We discard this solution. So how much can be the gain? What are we fighting for? How many? How much? As you can see from this picture here, that compares lift coefficient for two different airfoils, difference is approximately 0.3, 0.4 between points of same angle of attack. And when we divide by maximum is 2, we can say that improvement of lift coefficient achievable due to numerical optimization is close to 15–20%. So this is a realistic value. What we receive by optimizing airfoil numerically. It's not for all airfoils, not possible. It's just one example. For some airfoils, this optimization is still possible. For another airfoils, not. Okay, modern airfoils, they have they are on the limit of optimal operation. If you take any airfoil commercial last generation, you will see that it's not possible to optimize anymore because it's already were used all ways to optimize it. All geometrical possibilities were simulated. But for all the airfoils, it's possible still to provide such optimization. Okay, as I told you already, there are not just the geometrical restrictions, also restrictions on required lift, required thickness, angle of attack, restrictions on velocity. So there are many parameters which are influencing on optimization process. So it means that there is no one best airfoil for all applications. Maybe some airfoil is better from one point of view for one Reynolds number or one Mach number of flight. Another airfoil will be better for another Mach number of flight. So this is why there are hundreds, maybe already thousands of different airfoils, and modern airfoils are still being elaborated because of this reason. Please do not forget that since aerodynamics has more than 100 years, there is a huge number of already created airfoils. So if you need for your own project to create or to use some efficient airfoil, depending on parameters of flow and other conditions, please do not forget that you could use airfoil already created. You do not need to create your own structure because of several reasons. First of all, it's very time expensive. And second reason is it's possible to make some error, which you will discover only after you build physically this object. Modern airfoils, they are not just optimized numerically. After received, for example, by NASA profile of LS10417, of course, a set of tests in different flight conditions, different flow conditions is provided with the very high quality equipment and a series of tests, not just one or two tests. So all these parameters on modern airfoils, they are proven experimentally, not just numerically. This is why I tell you to save time, and if budget is limited, I recommend to use available airfoils instead of creating airfoils. It's a huge work, it's a big work. It's a very important work, but only if you have all necessary resources, time and money, you can work on this area. Nowadays, I think to build new profiles, to create new profiles, it's tens or hundreds of millions of dollars of research for each geometry. So this is more or less estimation of costs to be invested to find some geometry. For 99% of cases is not worth to do, but still very important. Anderson likes this figure 38. This is an old figure which Anderson showed on his book since the first editions. It's a triangular mesh around airfoil, a way to calculate flow around airfoil. Nowadays, such unstructured meshes are not used anymore because there are better methods of mesh construction elaborated. Disadvantage of such a mesh is a highly increased approximation error. What is approximation error? Is when you transform flow equations like Euler equations or Navier-Stokes equations to algebraic equation system. During this transformation, you take into account properties of mesh. And when mesh is represented in triangles, especially triangles with high skewness, when angles inside these triangles are different, you increase and significantly increase the error of this transformation from differential equation to algebraic equation. How much you lose is each time different. You can lose all the physical process. You can lose several percent. It depends on geometry, depends on simulation conditions, depends on what you try to evaluate. For example, if you try to evaluate pressure distribution, your losses would be very small. So your simulation would be accurate for such a mesh. But if you will try to simulate boundary layer and velocity distribution on boundary layer, probably you will lose all information. Boundary layer will be all too large, or properties inside would be incorrect. And since drag is a consequence of boundary layer, it can be overestimated or underestimated, usually overestimated. This same effect you can see if you will try to use mesh for inviscid simulation inside viscous flow model. If you have very few cells and you will try to simulate viscous flow inside this low density mesh, you will see same. You will see that exaggerated several times. Boundary layer and flow conditions inside are completely wrong, and shear stresses are completely wrong. So you cannot do evaluation from viscosity point of view and drag point of view. Here in unstructured mesh can be found same problem. So I would say that triangular mesh has to be used very carefully by specialists who know how to evaluate error associated with approximation methods. And it should be spent special attention on density of mesh around airfoil. We know that for most of the models, this triangular mesh allows calculation only with the first order of approximation. First order of approximation is a straight line. For example, you have one point in space and another point in space. And point I plus 1. So between these 2 points, there is a distribution of parameters. We know that flow is continuous, but triangular mesh allows us to just draw a line in the best scenario. In the worst scenario, it will be a step function. Okay. Not the best distribution of real flow parameters, because real flow can be different. Can be, for example, close to parabolic function in one direction, can be a parabolic function, different shape, right? So there are a lot of uncertainties when we use first order of approximation. We do not know exactly a lot of information in this region. This region can be big. So disadvantages of triangular mesh are well known. This is why I do not recommend you to use such mesh in your real simulations. You can read about these disadvantages in the book of Anderson, Pletcher, Tannehill, and also in other books of modern applied aerodynamics. I think I ordered in our library to buy these books, but I don't know if they were bought or not. But let's see, let's expect. Or better, there is a lot of information in the internet, and we can use for free a lot of info. We can receive for free a lot of information. So disadvantage of such mesh is increased error of approximation, requires additional competence of person who is using and must be very careful of using this type of mesh. Advantage of this mesh is that you can simulate curve geometry. And it was one of the first approaches in numerical methods to simulate complex geometries. Okay. Some results related to optimization. This all is concerning optimization of geometry of airfoil from initial geometry to the current or target geometry. I think target and current are almost same, right? Because how you know what is your target? Your target is to optimize, but you don't know the shape of this target. So for me, it's a bit confusing, this figure. Of course, we are trying from aerodynamic point of view to find lift to drag maximum. This is our target, but we don't know how will be distributed points in space. If we knew our target in space, we would not provide any optimization. We would just simulate one time. So in terms of pressure coefficient distribution and in terms of shape of airfoil, can find significant difference between initial geometry and final geometry of simulation. And these changes, they result in significant improvement of airfoil performance, as you already saw from previous picture, can be 15–20%, more or less in this range, improvement of lift coefficient. And in many cases, improvement also of drag coefficient. Another important aspect is also flow separation. We must reduce volume of flow separation, strength of flow separation. We must have as long as possible flow attached to our airfoil. And this is another objective of numerical simulation in many cases. So airfoils working at high angles of attack produce high value of lift and high lift to drag ratio. Anderson explains this from point of view of boundary layer. I think we can spend some time on this as well. I do not see any question for now. Please let me know if you have some questions. I would like to make a break 1 minute. I will take a glass of water and we will continue from this point. Okay, I'm here again. I see no question in comment, so I can continue probably. Approximation of boundary layer applied to airfoil is the following concept. Since our airfoil usually is thin and airfoil is directed to flow, so inclination of velocity vector is also small, we can assume that this airfoil boundary layer is similar to plate boundary layer on a flat plate. Of course, in real life is different. On upper and lower side, different. But just for first estimation or rough estimation, we can use such approximation. We will assume that our airfoil is represented by plate. We know quite well distribution of boundary layer on flat plate is a classical task solved by many different studies. And for example, for laminar flow, from our previous examples, we saw that thickness of boundary layer can be defined as function 84, and skin friction on this flat plate on laminar flow can also be defined on equation 86. For both of these cases, we see that thickness and friction coefficient are proportional to some constant coefficient and reverse proportional to the Reynolds number. In case of thickness, this Reynolds number is calculated by a coordinate x. And in case of friction coefficient, since it's a characteristic for complete airfoil, Reynolds number is calculated by chord size. Reference value, reference size is a chord size. Thickness of boundary layer is increasing. This is why we have also x in numerator. We have x in numerator, we have x in denominator. So once we simplify this, we will obtain something like square root of x. Let me try to write here. It's 5 multiplied by square root of x. And here, square root of viscosity. And in denominator, we will have square root of density v, like this, constant values. So all are constants except x. This is why shape of boundary layer is similar to this, to say, function of square root of x proportional to this function multiplied by a coefficient. Okay, so it's a coefficient multiplied by square root of x. Just that simple. And skin friction coefficient is just a constant for a flat plate or for airfoil. Constant proportional to size, proportional to velocity, or reverse proportional to velocity density. For turbulent flow, we have similar estimation. In this case, since turbulent flow is more complex, functions are also more complex. Reynolds number not in square root, but in power, 1/5. And this is also empirical coefficient, same as 0.37, 0.074 are also empirical coefficients. Thickness of boundary layer is also proportional to coordinate, as we saw on previous case. So it will increase with increase of coordinate. And Reynolds in power 1/5 is not increasing so fast that coordinate. And the skin friction coefficient remains to be constant value because Reynolds calculated by port size is a constant, so there are only constants here. Skin friction coefficient is constant, and the thickness of boundary layer is changing with the coordinate. We know that there is a transition between one and another regime. Between laminar and turbulent regime, there is a transition. Transition point is when thickness of laminar boundary layer is equal to thickness of turbulent boundary layer and also is inside the transition Reynolds number. So we can have these two parameters. Transition Reynolds number is a value calculated experimentally. If you remember at the beginning of aerodynamics, we had a graphics of Reynolds number versus friction coefficient. Probably could go back to chapter 1 and see these graphics later. It was first laminar friction coefficient, then transition, and then turbulent ones. And transition can occur in different values of Reynolds. So it depends on several parameters. This transition, quality of surface, can be turbulence inside incoming flow, can be, I think, temperature influence a lot on this distribution because viscosity is also changing significantly with change of temperature. So there are several parameters influencing on transition process from laminar to turbulent. And another limiting factor for us is thickness of boundary layer. When these two thicknesses are same, transition happen. Pay attention that turbulent boundary layer grows faster than laminar boundary layer. We can see it just analyzing formula because laminar boundary layer is proportional to square root of x, and turbulent boundary layer is proportional to x powered by 1 minus 1/5, so almost linearly. So bigger power. Flow separation is another concept which Anderson takes into account. This flow separation is strictly related to viscosity. Flow separation can be seen not just on flow lines, but also can be seen on distribution of pressure coefficient. Flow separation happens originally at a region with negative pressure coefficient, and at a region, it happens because of pressure gradient. When we have high pressure, let's see here on this figure, high pressure at zone, lower part of airfoil, high pressure, let's assume, because everywhere on the lower side is pressure higher than on the upper side. Because of this, we have lift, right? So pressure below must be higher than pressure above. And this is a zone of high pressure. Maybe it's better if I make it red. Okay, high pressure. And lower pressure is here, zone of lower pressure. And so there is a pressure gradient quite significant. At some point, these two zones will interact. Flow from high pressure region will try to impact and go against flow because it's the source of flow acceleration. Pressure gradient creates flow acceleration, and it will try to go against in a region of low pressure. It will not go in, it will not see other regions of low pressure nearby. So the closest region of low pressure will be this one. And since pressure gradient can be significant, flow in this direction can start. And when this flow will start, not just flow by itself, but change of pressure, okay, inside the boundary layer. Since velocity is very small, change of pressure can happen quite easily. This pressure will start to rise. Will start to rise on small region here. Will start small flow separation, and then this pressure rise with increase of angle of attack will distribute further. So pressure on upper and lower side of airfoil will be equal because it happens inside almost zero velocity inside boundary layer. And because this pressure is high, flow separation appears. Flow separation, flow goes in this direction. Since flow goes in two different directions, at some point they should interact. And flow separation starts. Higher pressure difference or pressure gradient, higher will be these forces to provoke flow separation. Okay, let's go back here. Different pictures representing pressure distribution. For us, probably this one would be interesting. It's a relative pressure with for two different processes, with separation and without separation. So there is no pressure gradient. When there is flow separation, pressure is equilibrated with the external upper and lower side, so there is no pressure gradient. And when there is no pressure, there is no flow separation, pressure gradient is large. And going to see general distribution of pressure on the airfoil, we observe the following: that without flow separation, sorry, I'm already tired a bit. Last lecture for today. Without flow separation, we have different pressure on upper and lower side of our airfoil. This one on upper and this one on lower. And these 2 points are very close one to another, since pressure gradient is a source of flow movement. And these 2 points are very close. Pressure gradient is extremely high. This is why flow from one region to another happens, because points are close, pressure difference is significant, pressure gradient is high, small flow separation starts. Everything starts from small and then increases with the increase of angle of attack. For separated flow, you see equilibrium between upper and lower side pressure. Okay, and exactly at point of trailing edge, and then this separated pressure, of course, is naturally decreases because flow goes in opposite direction. And there is a region of flow separation. We cannot say here from this picture where exactly flow separation starts, at which point, but we see that pressure acts against the flow. So it provokes flow in backward direction. For both separated and not separated flow, on the lower side of airfoil, pressure remains same. You can see that on this zone below airfoil, pressure is same for both cases, separated and not separated. But for us, more important is what happens on the upper side of airfoil. It's completely different picture for both these, for two cases, right? And because this difference on the upper side of airfoil, we have difference in lift. Lift on attached flow and lift on separated flow as a result of pressure acting on the surface. Some data about skin friction. Skin friction coefficient on airfoil and the flat plate, you can see how close or how far are these data. For flat plate, black line, thick black line is smaller, underestimated friction coefficient. For NACA airfoil, friction coefficient is bigger because airfoil shape is curved. We already knew that would not be possible to exactly calculate such friction coefficient, right? But it's at least it's some estimation. Here, fluent RSM and blows are two different computational models used to calculate. They are, I think, CFD models, two different CFD models to calculate CF coefficient. Not exactly corresponding flat plate to airfoil, but at least giving some information how much could be the value. Okay, I would like to finish for today because this real case or discussion about flow over airfoil for the real case will require a lot of time. So probably would be better if we start from this point. Next time we are quite good going on our schedule. Please let me know if you have questions. I will be glad to answer. And if you have questions about simulation or other things related to aerodynamics, please. Please do not forget that work 2 deadline will approach soon. So please deliver result or at least ask questions about work 2 who has problems to simulate. I know usually many people have such a problem. And do not forget we have monitors in one monitor, Artur, in aerodynamics. He's very experienced in simulation. Could ask him as well. I talked with him recently. Not many people asked help. Do not forget that we have support from Artur. Okay, Rafael. Good. I see no questions. Please have a nice evening, and we will meet on Thursday, same time. Continue talking about real case of flow around airfoils than around other aerodynamic bodies. And I hope on Thursday we can finish chapter 4 already and go to chapter 5. Thank you very much for participation, and see you next time.
Professor, can I talk to you about my work 1 feedback? I know you did this last class, but I couldn't come.
Yes, of course. So if who has no questions about work 1 could be free, I will stop recording. And who has questions about work 1 or work 2, we could talk here on this meeting. Okay.